In the circuit shown, this one, take the inductor to be a 1 microhenry one, the capacitor 100 picofarads. The arrow through the resistor indicates that the value of it is adjustable. For convenience, use M to represent millions. Write, for instance, S plus 10M instead of S plus 10 millions. Let's work on part A. Determine the value of that resistor that yields critical damping and compute the resulting transfer function from this input Vi to this output V0, G of S. Briefly, explain whether increasing that resistance value above the one computed results in underdamping or overdamping. Let's work that out. To find the transfer function between Vi and V0, let's compute V0. V0 turns out to be the product of this current of the source multiplied by the impedance of the 3R, L, and C in parallel. V0 is that current 4 times Vi divided by 10,000 multiplied by that impedance Z of S. But that impedance, as any impedance, is the inverse of the admittance, 1 over Y of S down here. So that is V0. And Y of S, being this a parallel, is the sum of the admittance of R, 1 over R, the admittance of L, 1 over SL, and the admittance of the capacitor, which is just SC. If we divide both sides by Vi, we have V0 over Vi, the transfer function G of S that we're looking for, this one. Simplifying, that becomes exactly a form of transfer function we're familiar with. However, what we want is to choose R so that the circuit is critically damped. Well, when we use Laplace transform with 0 initial conditions, it is as if we were using Heaviside's P operator. So the denominator here gives us the coefficients of the second-order differential equation that characterizes that circuit. You see RLC, L, and R. Those are also the coefficients of the characteristic equation. Let's write the characteristic equation, and it would be RLCB squared plus LB plus R equals 0. That is our characteristic equation. The roots of that equation are the eigenvalues, but in this case we have only one. We have critical damping, or at least we want critical damping. Well, remember, what we have to do is make sure that the discriminant of that quadratic equation is 0. The discriminant is this coefficient square, L square, minus 4 RLC times R, minus 4 R square LC. That's equal to 0 because we want the system to be critically damped. From there, we solve for R. Let's see. That term is 0. That means that L squared is equal to 4R squared LC. We simplify by L, divide by C, divide by 4, take square root on both sides, and we have R has to be 1/2 of the root of L over C. Substitute L 1 microhenry, C 100 picofarads, and you get that R has to have a value of 50 ohms for the circuit to be critically damped. The rest of the question is, now that you've chosen 50 ohms for R for critically damped circuit, what happens if R increases? Well, if R gets bigger than 50, this negative term will get bigger than L squared. The discriminant will go negative, and the two eigenvalues will be complex conjugate. The system will become underdamped. and I wrote that here. If R increases, the discriminant becomes negative, the eigenvalues go complex, and the circuit underdamped. The last part says find G of S, because this is in terms of R and L, but we want to have that transfer function for the critically damped circuit for 50 ohms, that is. Substitute over here R, L, and C for the values we found and the ones given, and the transfer function G of S is 4 million times S divided by S plus 100 millions squared. And that is parte.